So we're recording. Let's get started. Yeah, so this week we are currently week 11. This is week 11. So next week, week 12, you have exam 2 on Tuesday. Remember, it's closed notes, but you're allowed your cheat sheet. Exam is comprehensive because it's basically cryptography builds on previous ideas. But it's going to cover, we finish RSA, asymmetric encryption, and also symmetric encryption, all those principles, and actually a little bit of signatures. Yes.
Is it going to cover everything?
Yeah, it's comprehensive. Yeah. So from week 1 to now. Yes. Yeah. Um, and so yeah, so that's the plan. To this week we are covering Diffie Hellman, and then as an algorithm, which is pretty simple. We're not going to spend too much time on that, and you'll see that these, if anything, it's because it helps us to see that these algorithms are similar. The math is all coming from the same place. Actually, Diffie-Hellman was the first, then it went away, and now it's back. So it's kind of like that. So, but today I'll just give some intro of it, and then I'll expand on it maybe on Thursday. And then the other topic today is certificates, which we've started signature certificates. So I'll do that. And then the lab this easy, I think, is very easy. It's very easy. So the lab this week is very easy. And that's because you do have an exam coming up. So I'll give that. We should be able to do that on Thursday and finish it without any issues. I think there's only like 3 problems. And then you can just ask questions, or we'll do it like a semi-open lab, and whatever issues you've got before the exam on Tuesday. Then on Thursday of next week, week 12, is when you will do your PyCrypto demos, that homework assignment. So that's already posted, I believe. So if we go to content, so we are about here, this one, right? So this is complete, but I've given you, we finished this Thursday, past Thursday, and I've created the homework, and you have plenty of time, but the demos will be a week from this Thursday, right? So that assignment I'll sit with the partners and I'll ask you questions. Remember what I said. I'll ask you to bring up a text file, put in the message in there. So I'll change it, like I'll say like, this is a new movie, something, something, something like that. And then you have to do problems 1 and 2, which is essentially achieve confidentiality, integrity, but this time also authentication. And I may say that you need to do all that in one shot. Got it? So that's what I'm testing. So you'll need to have all the proper keys, everything, and so on. Right? But practice it, because in the past, students always did it with a specific sentence. They thought that they were going to use that sentence. And then when I changed the sentence, it doesn't work for some reason because they had some kind of error. So assume I will change your sentence. So make sure to practice for that. Got it? But yeah, it's just a lab. It's really I think in cryptography, these things are important to make sure you actually understand the concepts, because sometimes you do it and you don't really. So, but yeah. So we'll do that. And then, like I said, the scavenger hunt is going to happen sometime in the future after these demos. So week 13 or 14. This is the week that we're covering today. Kind of several topics. It's interesting though. I think you'll find both of the algorithm very simple and interesting. We're going to do it on the whiteboard first, then we're going to implement it in Python. I could use this at some point, right, in the scavenger hunt. So be aware of that. But it's a nice type of a key exchange also, right? So remember, in asymmetric, this second third of the semester, that's what we're focused on. It's like an amazing thing, right? So how do you get security out of nothing? Just math, right? And that's essentially what we're doing. So this is another type of key exchange, but it has some limits. In the past, at least, some of them have been overcome, etc. So these algorithms are very powerful, and sometimes people have clever ideas that bring life to them again. Okay, if you notice, we are, getting to the end of the semester. So I remind you, term project, Please form your groups, 2 or 3. Start looking for a topic on cryptography. You can shoot me an email if you'd like with your team members, 2 or 3 ideas of what you want to do. Remember, it's not worth a lot of points, 10% of your grade. You can code or you can just install some program in Linux that relates to cryptography. We talked about this a lot. Students have done quantum computers, quantum cryptography, things like that. All right, and then essentially, so we have Diffie-Hellman today. We only have 2 algorithms left. Um, 2 algorithms, and then we have applications, of course. So we are going to do HTTPS, which is the client server architecture. This is a really great lab. Goes as far as certificate authorities. So this is probably week 13. PyCrypto Dome, Big Num Crypto. I usually do this as a bonus lab. So anyone that has missed a lab, has a 0 or something, this is a good opportunity. Or if you want extra points. And then applications such as cryptography for defense of denial of service attacks, for malware detection, and of course the last topic that I will cover, which is application related, is blockchain and cryptocurrency. So I'll talk a little bit about that, how that works. You'll see that hashes are there, integrity, some of those principles, and also elliptic curves. So the last 2 algorithms left, right, in cryptography are Diffie-Hellman today, and then elliptic curves, which we will cover in a future class, after the exam. And that's your last algorithm. And then after, we're just kind of doing more application things, etc. This week's lab is on openssl also. So today and Thursday, we'll be using openssl with the VM. So I'll boot that up. All right. Obviously, remember cryptography. I would imagine there should be a cryptography 2 that looks at all the quantum algorithms, but on the event that somebody invents an actual quantum computer, you guys will have to relearn all this and learn about quantum computers. Hopefully, I will not have to do that. Hopefully, I can retire before that happens. All right. So yeah, so that's kind of the plan. Okay. So let's get started with the first topic, which is going to be Diffie-Hellman. So I'll go over the algorithm, kind of how we did with RSA, and then we'll implement it in Python, and should be pretty straightforward. So I'm going to switch over to the whiteboard for this one. Okay, so here we are. All right, so this is very similar. We're using the modulus operation. There's prime numbers. Remember that the history of this is that 2 scientists kind of had this question: how do we exchange the key securely? They started formulating ideas. They came up with math that actually looks a lot like the RSA algorithm, right? It has some of the operations, and they figured out some things that they could do, but it just didn't have, all the applications that RSA has. So RSA then later came in, and it was just more powerful, took over. But this one now has found some usage, which I will discuss in another lecture. So, but let's just start with the very basics and simple things. So why is it called Diffie-Hellman? Because of 2 gentlemen, Diffie and Hellman, right, who worked together sometime in the 70s to propose these ideas, and they're still around today. Okay, so let's take a look. So this is going to be Diffie-Hellman. Which colors here? Red. So Diffie-Hellman, so around the 1970s, and this is for key exchange. Part of asymmetric encryption algorithms. Okay, so we're going to assume once again we got Bob and Alice. Okay, so we're going to start. Let's look at the algorithm. And by now, you guys are able to implement this, even if I don't give you any code. I guarantee you can just write the code. It's so simple. Same operations. But we'll do it on the VM. So step one, let's say, step one, um, one. All right, so you have Bob and Alice, and they have to agree on public parameters. So they're going to agree on essentially a prime number. So you need to define a prime number. And then you create a list. Create a list from 1 dot 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 to p minus 1. Do you see that? And then from this, you're going to derive the set of parameters, that you can select. So let's assume from here, from this list, right, that you're going to select two values. Bob selects a value, Alice selects a value. All right, so let's just say select Bob and Alice agree on public parameters. So Bob and Alice agree on public. Remember, when I say public, I mean something that's available to everyone. It's not a secret. Okay. So on public parameters, which are going to be P, the prime number, and G, another value. Okay. Then after that, in step two, from that list that they can create, let's just define it like this, where this is the P prime number. They select two values. And we're going to call this group Z. So this is a group Z. And from that group, they randomly, from a group C, they select two parameters. So for instance, Bob selects A and Alice selects B. So from here. Okay, so select these two parameters. Now, in step three, a private value, and now let's define these parameters. So these are actually private parameters. So a private value A, private value A has a public value, uppercase A. Has a public, or it's associated, has a public value A. And remember, they've also agreed on a prime number and a G number, right? So where they're coming from, let's not worry about that yet, but just remember the parameters. So they've agreed on a P and a G, P and G. And now they, a private value A is associated with a public value A in the following way. So for instance, so let's say such as, right? So a private value A has a public value A such as, and here it is. So the function would be A equal G to the A mod P, which is the prime number. Do you guys see that? So essentially, this is how they can compute the values, a public A, given the G and the P that they have agreed on and the A that they selected and the B. All right, so a private value A has a public value uppercase A, such as this expression here, where this one, the P, is prime, the selected prime number. All right, so let's look at step 4. Step 4, so we repeat the process for Alice. But let's say this value A, uppercase A, is sent by Bob to Alice. And that's why it's public. Okay? So I'll make the comment here, A is public. All right? Then we have step 5. So now we have the public value associated with lowercase b is similar. So let's say, how do we write this? A private value b, a private value b, lowercase b, is associated with or has a public value b, such as has a public value b, value uppercase b, such as, and you might imagine it's a similar relationship. So this is going to be b equals g. Remember, g and p are the two agreed upon terms. G to the lowercase b mod p, which is prime. If you look at this, it looks a lot like the way we encrypt and decrypt with RSA. Pretty much the same. So you can see that it's the same math, but RSA just created a slightly better approach, more powerful. But this one is also useful. All right, so now we have that the public value associated with lowercase b is this one, b equals g to the b mod p. All right, so now let's move on. Step 6. Step 6. Now, in Diffie Hellman, B is sent to the owner of A and is public. B is sent to the owner of A, of lowercase a, remember A is private, and is public. Okay. And now we do step 7. So Diffie Hellman works by combining either public value A or B with the other private value. Okay, so that's essentially what it is. So let's write this down. So Diffie Hellman works by combining either public value in this case, uppercase A or B, with the other private value. Value. Such that we have something like this. So essentially the uppercase A combined with the lowercase b. Do you see that? That's essentially the trick, so that they'll have parameters that will create a secret key that they both have. So this is the idea. Okay. So a simplified way of looking at this, okay, would be that, and let me do this actually. So I'll do this in the next slide. So you have Bob and Alice. And what happens is, one would have A to the B, right? So that would be, in a simplified way, G to the A to the B, which translates to G A B. And Alice would have B to the A, which would be G to the B A, which is G to the BA, which is G to the AB. So as you see, both turn out to be the same. Do you see the idea? So this is the underlying, simplified way of how this works. But essentially what you want is that both of these are the same. And guess what? Once they have, each of them has this value, they can from there create a key that is the same. And they can start doing encryption. Do you guys see the way it works? So this is asymmetric encryption. Remember, just key exchange. That's all you're doing. Okay. So we'll do an example of this. But let me make a note here. We'll do an example and then we'll do it in Python just to make sure it works. So the resulting value the resulting value GAB is the shared secret. It's the shared secret. And of course, this can be used to generate a symmetric key. So this shared secret can be used to generate the symmetric key. And once you have that symmetric key, then you can use your favorite AES, DES, whatever it is, to do confidentiality. Okay? And you achieve key exchange, essentially, with this approach. A few of the downsides of this is that it has some limitations. This algorithm was, so just a few of the limitations that it had historically, and then we'll look at the example. So downside, number one, it doesn't work with just any prime number. So this has to have only a set of specific prime numbers. So that's a restriction, okay? Obviously that, hackers could break it more easily. So the approach, the approach does not work with just any prime number. Prime number. Okay. Um, or base number G. And remember that we had to pick a P and a G, right? So it's got to be a set of numbers that we select. Or base number G. So if you think about it, we're always looking for sets of values that we're picking, right? So we pick up, it's got to be a prime number, but it's got to be a prime number from a specific set. It's got to be a G that corresponds to it from a specific set. This is important because a lot of the algorithms work like this. Another algorithm that works this way is elliptic curves. Elliptic curves also needs a set of initial values, and those initial values come from what? A curve. So it's some kind of geometrical, you have a specific function that creates a curve. There's a set of math that um, only works in this curve. And based on this map, in this topology of this curve, is that you extract values that are initial values. Does that make sense? So you can see how these algorithms historically have been trying to do the same thing, right? They use operations like mod, prime numbers, and then you pick values from with some scheme. So here we have the initial one with Diffie-Hellman, or you have now the more modern elliptic curves, which are considered to be. And by the way, there's many curves out there, but only a handful of them are considered to be secure. They're highly studied, reliable. Other curves, there's people, you might have, I don't know, what's a coin? Meme coin, asparagus coin, right? Something like that. And they're using some kind of elliptic curve that who knows where they got it from. You got to be careful with that because you don't know how secure it is. Does that make sense? So you see how you're always looking for ways to extract certain numbers that provide a lot of security. The downside traditionally of Diffie-Hellman, the approach does not work with just any prime number or base number G. Okay, I do have some commands that we will explore once we switch over to the VM. Okay, so we'll play with those in a little bit. But a few comments also as we're talking about the downside of, sorry, this is a 2. Okay, so we're talking about the downside. The other one is RSA is considered to be faster. So RSA, at least historically, was faster. Elliptic curves are also fast, and the numbers are smaller than RSA. As you know, one of the key things with RSA is it's got to be massive, right? The value that we select initially for the C to calculate the prime numbers, what was it in our examples? 2048, if you remember, right? Bits. So that was pretty big. So Diffie-Hellman would be considered too slow for a key of the same size as RSA. So essentially, RSA would be faster. And as we've discussed many times in cryptography, it's always a balance between security and performance, speed, essentially. All right, so I think now we're ready to do a problem. So we'll do an example of this, and then we'll implement this example on the VM and go to the VM and do, various things. So let's do an example just to illustrate. Let's call it problem Diffie-Hellman. Okay, so this is our problem. Again, I'm going to use Bob and Alice. So I'm going to go with steps. Step one, we've got Bob and Alice. And let's just say Bob and Alice agree on the public parameters. Agree on the public parameters. P and G. So in this case, P is going to be the prime number. It's going to be 23. 23 should be prime, right? Yeah. So P is 23. And the corresponding G would be, in this case, 5. Yeah, so 5. Okay. Step number 2. Okay, so we've got these parameters. Remember, that's your G to the something mod prime. So now we have step 2. Okay. So in step 2, they have to get their A and B, right, from a list called Z, from 1 to prime. So let's assume they select, and these are private values. So in step 2, Alice gets a secret, call it secret or private, and that's going to be A equal 4. Okay? I'm using small numbers here. Then we've got the same for Bob. Bob would select a secret, which would be B equal 3. Okay, so they've got the parameters. So that's it. Now, once they have this, they have agreed, they've selected the numbers, and now they can calculate the public values A and B, which they exchange. And once they exchange those, they can compute the secret value. So that's the goal here. So let's go to step 3. Step 3. So here, this is going to be, we're going to calculate A. So who had lowercase a? Alice. So Alice had lowercase a. All right, so then she can go ahead and compute the public A, which would be G to the A mod P, which is the prime. All right, so that should be then G is 5. G is 5 to the A, which is 4 mod P, which is 23. Do you guys see that? Make sense? All right, so remember, they both have G and P. They had their selected proper A's and B's. And with this approach, now they got A. A is, in this example, 4, and it is public to be shared. Okay, now we have step 4, or next part of the process. And this is going to be Bob. Oh, right. Great. Okay, so now we're going to do Bob. Bob. Okay. So Bob does the same thing, needs to calculate uppercase B, which is going to be the public. So Bob uses G to the B mod P, just like that. Okay. So this should be G is 5, correct? And they've agreed on that term. B is 3. So B is 3 mod 23. So this calculation, B should be 10. And it is public. Do you guys see that? All right, so that's the process. Now, Alice, yeah, so then Alice sends A to Bob, right? So if I give you this problem, you have to remember what you have to do, right? So how to exchange it. And then Bob sends B to Alice. Whoops. Like that number. So 4 and 10 are going to get exchanged. We can even do something like that because they're important. All right, now we go to step 5. So here, let's start with Alice. So Alice receives B, from Bob. Okay, and now she can proceed to calculate the secret message. Let's call it S. And this is going to be should be the same for both. All right, so the way that you compute this one is that similar approach. Notice how important this equation is, right? We use it everywhere. What a math discovery. So we got B to the A. You see how now she's combining her private A with the public B mod P. And there you go. So now S should be, what was B? B was 10. So B is 10. Lowercase a is 4. So it's 10 to the 4 mod prime, which was 23. Okay. And we compute this S, and it should be 18. This is the secret to use. Now we repeat this, step 6. Okay. So that now it's going to be from the other end, Bob. So Bob receives A. Eves A. Okay. And Bob then is going to compute the same thing. So S equal, in this case, now uppercase A to the B mod P. Do you guys see that? So that's essentially how this works. And we can plug in the values now. So S, A is 4. So A is 4 to the B, which is 3 mod 23. And that should give you an S equal to 18. And as you can see, now they both have a value that's exactly the same. And so they can proceed from there to derive a password with some algorithm or something like that they can use. Okay. Yeah, that's it. So that's Diffie Hellman. At least our first simple example. We might look at this a little bit more deeply, but that's the general idea. Okay. So this can be, we can use openssl as well to try this out in a little bit. But let's go ahead now and implement this from scratch in Python. All right, so we're going to switch over to the virtual machine, make sure that these values actually come out, and then we're just going to start elaborating on the functions. So I need to switch over to the virtual machine. So I'm going to go ahead and stop this one. I'm going to hit share screen. And now I'm going to go ahead and start the VM. Okay, so let's start the VM. Okay. Keep in mind the prime number that you select initially is a very big prime number. Like think 600 digits. It's a really large prime number for this to be somewhat secure. All right. So let's hit on seed. Let's log in. Terminal. Let's open up a terminal, go to our folder. Okay. So I'm going to navigate to the desktop. And then I'm going to go into fall 2025. Here I'm going to create, this is different from RSA, so I'm just going to create a new folder. I'm going to call it Diffie Hellman. Hellman. All right. Okay, so now let's create, I'm just going to create a script, but really you'd have two scripts, right? One for Bob, one for Alice. You guys can modify it. I'm going to call this one simple, call it toy, simple, Diffie Hellman, .py. Okay, here we are. So we need to, we would have an agreement on a P and a G. So these are parameters that are shared by them. G would be 5 in this example. Okay. Then after that, we would have, they would have Alice have her section. Alice, oh, let's do a comment here. Alice would have the value A, which in this case is 4, right? And then Bob would have the value in this case 3. Okay, so we've got A and B, the private values. Now we want to be able to calculate them. So in this case, this is going to be Alice's section. Oops. All right, so we need uppercase A, and we compute this just the same way we did this before. You should be able to do this already. G asterisk asterisk. Right, that's why we can raise something to the power of something. So G raised it to the power of A, just like I did in the equation. Then mod, right? P, the prime number. So in this case, P is 23. All right, so we do this computation and we can print A. Right, let's try this one. We're gonna run it. Python 4, right? So that's what we had before. Good. So now let's try the other one. So now we're going to do the side of Bob. So this is going to be Bob. Bob needs to generate uppercase B. So it would be the same thing. G to the power of lowercase b, just like that. Okay. And this is going to be mod P, which is prime. Okay, and we do the same thing. We print B, so we can say B is comma uppercase B. All right, so let's run this. Control X, Y, enter. And you can see B is in fact 10. Okay, so once you have this, then they would remember send this via email or however, and now they can proceed to calculate the shared secret so that they can establish their communication. They want to do this again because they feel their password is compromised. They calculate these values again, resend them, etc. Right? So that's essentially the idea. So now let's go here and let's corroborate that the S's are in fact equal. So we're going to do Alice, the side of Alice first. Alice, just like that. So here's the secret S. I'm going to, just to differentiate them, I'm going to say S, S, Alice, just like that. And then we're going to print both. So this should be B, right? The uppercase B that I received to the power of A, which she has, mod the prime number, which is P, which is at the top, and they both have, and is 23. Okay, so that's her secret. So we're going to say S Alice and print it actually. Print S for Alice. Just like that. Okay, let's see. Let's run this script. And you can see it is in fact 18. Make sense? Now we repeat the exercise for Bob. Okay, so now this is going to be Bob. So we're going to call this S underscore Bob. To compute this one, it's going to be, so Bob got the uppercase A from Alice. So it's going to be A to the power of lowercase b, which is Bob's private value, mod prime number P with a prime number. Okay, and then we're going to print this value, and they should match. S for Bob is going to be S underscore Bob. Okay, so we try this. Okay, and there you are. So both of them are 18. So they, in fact, have a way now of creating a shared secret. So it's, this creates a shared secret. Before we had a secret, right? And we would just encrypt it and send it and achieve confidentiality for the key exchange. Okay, so remember on the scavenger hunt or the exam, I could, give you these things. That could be one of the three keys that you need to break, right? So how to get this number. Are there any questions, guys, on these ideas? Questions? All right, good. So let's take a look here. I have another example, so let's try this one out just real quick. It should be just plugging in the values. All right, I'm gonna reuse the same code. Okay, so assuming a P of 11, which is prime, and a G of 2, and then I assume an A of 9 and a B of 3, which is already 3. Let's recompute everything. 7. Do you see that? So it matches. So that's two sets of numbers, but you have to have the right set P, Q, A, and B. Do you see that? And once you have that exchange correctly, then they can do the cryptography. Okay. So yeah, so that's a simple one to get started with Diffie Hellman. Okay, so now yeah, so now we're going to switch gears a little bit to just openssl. Play with that a little bit. So I think for Diffie-Hellman, it's something like openssl, and I think it's DH param, and then 2048. Okay, maybe. Oh, I think I started with something smaller. So since I don't know how long this is going to take, let's try with something a bit smaller. Let's see if we can. 256, maybe. And you can see this starts to give you some parameters, but it gives parameters in this type of format, right? So we need to have some functions to extract information from here. But let's just run one more. 512. Oh, really? Well, Mike, it's probably you have a better computer than me. Let me try 1024. Yeah, yeah, okay. So it provides the parameters. Um, let's do one thing. So one thing I have here in my notes is to run a performance check. So let's do time openssl dh param 1024. All right, and you can see there it gives us some metrics. So what we're doing is benchmarking you know, the param to generate those numbers. Now I'm going to do the same to generate RSA. I'm going to do time. So it took what, 18 seconds, 6 seconds, and 9 seconds. So let's do time openSSL. Oops. You can see what this time openSSL gen RSA. And we have to use the same size key. So I used 1024. Yeah. So what do you guys conclude from looking at these numbers? We're trying to generate similar size keys, right? Similar security. But what's your conclusion from looking? So this is a benchmarking example. Actually, on Thursday, we're going to do more benchmarking. So what would you guys conclude? Which one seems to be faster? RSA, right? So, which is consistent with what we had said, right? That one of the problems, the downside is that um, it doesn't just work with any prime number and number G, and DH is too slow for a key of the same size. And so you can see here, these took roughly 18 seconds, 6, 9 for different metrics, whereas this took 0, 0, 0 for the same. So you can see RSA already had an advantage in generating the key. Got it? If you think about it, when you're going to Amazon, you're not just creating one key once, you're doing for a little interval, and you do the exchange and everything. So that adds up doing that process. Okay, so now let's look at a few more openSSL commands so that we can start digging into some of these files. Like if you notice, we get values like these, we get values like these, okay? So we're going to start just learning a few of the openSSL commands to extract values from these files. And then we're going to get into certificate authorities at some point. All right, so let's generate a couple of keys just as an example. So this is just more generic to looking at these PEM files and extracting information from them. So we want to see specific parameters used in public keys, private keys, Diffie Hellman keys, etc., and even certificates. Okay. The key is that it's all coming from a PEM file. For practice purpose, we're going to first generate just a pair of public and private keys. Right. So let's try that. So openSSL gen RSA. And let me actually see what we have here. So let's dash L. All right, so we just have the Diffie Hellman, openSSL, gen RSA, dash out my private underscore key dot PEM. And we're going to specify that we want it to be 1024. Okay. Okay, hit enter. All right, so it did it. Let's do ls-l. Okay, there we are. Now let's run cat my private PEM, and you can see we have in fact a private key in this specific PEM format. So this is a problem, right? It's starting to become annoying that we can't really see what's in there, right? So we're gonna explore how to do that. Okay. So we have the private key. We're gonna generate from this given private key, we're gonna extract the public key. So we can do openssl for this example, RSA dash in, and we're going to take my. So one key thing to remember about the private key that I mentioned before is that even though it's D comma N, right? If you guys remember, in the PEM file, it actually, the PEM file stores the P and the Q. Do you guys remember? I mentioned that, right? So we have a lot of the parameters that we need to process and extract our public key. So openssl RSA dash in my private underscore key dot PEM dash pub out, and we're going to redirect to a file called my public key dot PEM. Okay, so we do that, so you can see that there. ls-l. Now I have two keys. Clear. If you notice, we can see already this one is 887, this one is 272, so it's smaller. We can visualize my public key. Whoops. My public key. Oh yeah. Public key. And you can see this is a public key, smaller in that specific PEM format. So the first command generated the private key, and the second outputs the corresponding public key. All right, so now let's say that we want to extract the number parameters from a PEM file containing a private key. So how do we do that? So we're going to do openssl RSA dash text, and then we redirect from, in this case, my private key dot. Okay. Do you see this, guys? So now I've taken that strange format, right? And I'm able to extract the values that match more closely to the mathematical formulation that we have discussed in previous lectures. So so this is important that you're aware of these values, given that I could give you a PEM file. Do you see what I'm saying? So for instance, does that make sense? Like I give you a PEM file and everything is in it. So what does that mean? So for instance, what is this one here? It's n, right? That's the modulus. Now it is formatted differently, so that's another problem that we need to address, how to change it, but which it can be converted. We have the public exponent. Notice 65,537, the familiar E exponent. This is the private exponent. So what would that be, do you think? Remember, this is the private key. Which letter in the equations would this be? D. Very good. Prime 1 and prime 2, right? And so on. So you have all these values and other computations and all coming from the private key. Does this make sense, guys? So this is how you can extract now from the PEM files the values. So if you're actually a hacker, like an actual, you were going to break RSA, you're gonna get a PEM file, right? So you're gonna go to a bank, not that you guys would do this, right? But you would go in a mock bank, find this PEM file, run these commands, get this output. So all openssl, proper implementation, and now you find that n, and what do you need to do? Factorization, right? So, whether you have a quantum computer or maybe you come up with some new algorithm or something, break it, and you're good. Obviously, here you don't need to do any of that because this is what? The private key. So you already have all the parameters. So I could do an example where I just give you this and you don't even have to do factorization, right? Everything's in there. Does that make sense? All right. So make a note of that. All right. So we did that example. I wanted to show you this because to effectively, truly be able to break things, you first need to extract it from PEM files, which everything is PEM files. Questions? All right, great. So let's look at the next one. So we're going to extract the, so we look at what the contents of private key were, right? Take a mental note. It tells you this 1024 bit. So that's very useful. Now we go back to our example, ls-l. We also have a public key in here, which is actually the one thing that you'd be able to probably, hijack or test in a defensive setting. So then you would do openssl. Let's actually clear this. Clear. So you would do openssl RSA dash text dash pub in. We redirect from my public key dot m. So you notice there's less information in this one, right? But very importantly, we have this. Is this a public key? Well, it says it's a public key. What do we know about the public key? It is a tuple of e comma n. So essentially you have e, and what is this one? That is n. You're in. Does this make sense, guys? Any questions on that one? So I do think on the GitHub, I have a little script, I believe. We had seen it before and I made a note of it. Let me see if I can find it. Cryptography. Yeah, so if you notice, I have, well, I can open it here probably. So I have a script called convert hex to decimal from my public PEM. So we're going to try that out. That's let's go here. This is a bit of a hacky script. Should work. All right, so let's go to the GitHub. Okay, and there should be, so here it is, cryptography. And we go to RSA. Okay, and this TXT file, I guess, click on that. There it is. So if you notice, these are just a set of commands to be able to extract the modulus, which is what we're trying to process. So if we look over here, this is in fact called a modulus, right? So this, I'm going to run a command that is going to extract this, okay, from the file, and then we're going to try to convert it to decimal notation. So you can type the same command. First, I'm going to create a variable in the prompt. For those of you that have taken 372, you know that the command line is like a programming language in itself. And so I'm just going to take advantage of that. So I'm going to do hex modulus. And remember here, you have to be careful with spaces and things like that. Dollar sign. Okay, and then I'm going to run the openssl command. I'm going to say openssl RSA dash pub in dash in, and then we're going to bring in my underscore public underscore key, my public underscore key dot PEM. Then I'm going to say dash modulus. I'm going to pipe, which is just a redirection, the results of this into grep. Pipe into grep. And I'm going to look for the line that contains modulus equal, like that. And then I'm going to pipe this into cut dash D, single quote equals single quote, space dash F2, and space, there should be a space. So exactly how you have it here, okay? So all you have to do is type this one, okay? So this command is I'm doing. Got it? This is just Linux prompt, the Linux command line utility. So this is just to make your lives easier, really. All right. Okay, so I extracted it, I assume. It should be in hex modulus. But I haven't yet converted it. So this just gives me the value itself. I think I have to put a dollar sign or something. Whoops. Yeah, and there it is. So there's the value. But we can, that's actually in good. That may be actually the value that we want. All right, so, but I do have an additional step, which is to format it a little bit better. And I'm going to use a scripting language called Ruby, just like Python. There's Perl. There's lots of scripting languages. So we may not have Ruby on these machines. I think I have Ruby, but You guys may not have it. So anyway, if you need to install Ruby, you would do sudo apt update. Just do this if you're having trouble installing it, right? So you would run this one first. Once you've run that, then you would do sudo apt install Ruby, okay? It's just a scripting language. You could probably do this in Python. I just don't happen to have this in Python, okay? So now let's run. Once you've done these two and it installs, is it installing for you guys? Okay. Did it finish or is it still going? No errors? Okay, perfect. So now let's go ahead and run the second part of this, which over here, so you can see there's like a part of extracting the modulus into the variable. There's, if you don't have Ruby, installing it, and then finally just running this to process and format appropriately the modulus. Why would you want that? Because maybe, now these are really large, obviously, but maybe I could do a modulus that has a 32-bit size. I don't think openssl actually will give me something like that, but let's imagine, right, that it will. Then I could, that n is small enough that factor db might be able to factorize it. Do you see where I'm going with this? Everyone with me? All right, so this is the point of what we're doing, or I could hide parameters in other places. The Diffie Hellman parameters, and you need to get them from the file. All right, so let's try it. So the last part, we're gonna do Ruby. And this has its own syntax. EOF, EOF, P, lowercase p, $, hex, modulus, okay, like that, and then dot to underscore I 16. This is just a formatting dot to, which you can see 16 to decimal. So it's converting to hex, then to decimal 2 S 10, like that. EOF. And there we are. So, oh yeah, that's right. So the one I got before was, what's the difference between these two? See this one that I got over here versus this one within the double quotes. What's the difference? There, hmm? Exactly. One is hex and one is not. All the examples that we have seen for factorization have been of integers, right? In the RSA algorithm, we got n's that were that big. Do you guys remember that? So, but the problem is it has to be factorized. Well, how do we do it? So the only alternatives that you guys have right now are FactorDB or the quantum computer example, which was pretty slow. And I would have to give you a smaller n for you to be able to factor. Something this big, I wouldn't give you. So do you guys get it now? So essentially what now from a PEM file, you are able to extract all the things that you need and arrive at an n, at least in the proper format, that could be factorized. If you're a secret agency with a quantum computer available, You grab this number, get P and Q, and that's it. You break all the encryption available. Okay? All right, so this is just kind of a small taste of what we can do. Yeah, so in both of the commands that we have done, we can see the parameters as the actual parameters that make up the key. We can also, so we still have a few minutes. We can also extract individual parameters. Okay, so I'm going to do another just example command with the public key. So another way of doing this is open SSL RSA dash text dash hub in dash modulus, and this parameter allows us to extract the modulus my underscore public key dot PEM. Oh, I did. Oh no. Okay. So I actually did this the wrong direction. I meant to do it like that. Oops. But sorry about that. But yeah, I may have corrupted the file. Let me. This one. Okay, that should do it. Regenerated the public key. There we are. Sorry about that. So this one, as you can see, yeah, so RSL. Actually, there it is. So it provides the modulus as hexadecimal, which wasn't available in the other file. You see that? So it makes your life a little bit easier. Okay. It's just different ways of processing things. Okay. And I guess now the final question is, and maybe this is like a challenge for you guys. So we had the Diffie Hellman. Didn't we have the Diffie? So we ran a command. OpenSSL DH param. Let's go with 1024, right? And we would want to extract the values from that one. Do you guys see that? So we'll do this in the next class. So it's almost 5:40. But yeah, that's kind of the process. So today we covered Diffie Hellman, an introduction to the algorithm, right? And then we started with OpenSSL. We'll continue with this extracting or generating files that contain parameters, but we need to be able to process the values out of there. All right, so let's stop here for today, and we will continue this discussion on Thursday. And we will have a simple short lab related to this. All right? All right, so I will end the video here.